So here's where things get a bit more fun in integration, and you might not believe me because you might not find maths fun at all. But trust me, this application is very interesting and very useful in methods and just in day-to-day life as well. I'm just joking, it's not that useful in day-to-day life depending on what you do, unless you want to find areas under curves for fun. And that's what we're learning today. We're going to try to find the area underneath curves. And you might be thinking, what's the area underneath the curve? Doesn't it just go all the way down to the abyss in y is equal to negative infinity? Actually, no. The area under the curve is kind of deceiving in terms of its terminology, but if you have the area under the curve, what it's talking about is the area bound by the curve and the x-axis. So you can see the area that I've shaded here. It's between the curve, the x-axis, and the x values a and b. So a is what we call our lower bound, b is what we call our upper bound. And if we wanted to find this area, an expression for it would be the integral from a to b of f of x dx. Now, a lower bound, b upper bound. You might not be familiar, or you might not remember what these bounds are actually doing. So what this is a definite integral. Definite integral, just as a reminder, is when we actually substitute in bounds to our expression. So what we do is we substitute in this into our integral, and then we minus the substitution of that one. And the difference between those two values is what we call our definite integral, and in this case, it's going to give us our area. Now, to actually illustrate how it's applied, what we've got is this really basic example where we have the function f of x is equal to x squared, and we want to find the area bound by the curve, the x-axis, and from x equals 0 to x equals 2. So how we do this is exactly the same application of this formula. What's the lower bound? It's x is equal to 0. What's the upper bound? X is equal to 2. And don't forget, you put the x values only, the y value doesn't really matter. That's kind of taken care of when we substitute it into our function. Now the function rule here, in this case, is x squared dx, and we just evaluate this. So how we go from this step to the next step is we find our general rule for the integral. In this case, we add 1 to the power, divide by that new power. We end up getting x cubed over 3. And you put your lower bound on the bottom of that square bracket, and you put the upper bound on the top of that square bracket there. Now from here, what we do is we substitute in the top expression, or the top value, and minus the substitution of the bottom value. So in this case, it's 2 cubed over 3. So 2 cubed is 8 divided by 3. And then we have 0 cubed over 3, which is obviously just 0. Therefore, we get 8 over 3 units squared. That is really messy units, but that says units if you don't believe me. So 8 over 3 units squared is the area underneath this curve. And you can see it's not a very big area. 8 over 3 is roughly 2 and 1, well, it's exactly 2 and 1/3. So 2 and a bit units cubed. That's because this graph is very enlarged. But you can just imagine, if you had to find this area without integration, this would be an impossible challenge, but integration makes it really easy to actually evaluate these. Now, this is a very basic case. We'll actually go to a more complicated case where you kind of just split up your area into multiple parts now. Now, here's an example of a more complicated area where you can see we have portions that are above and below the x-axis. And you might be thinking, can't I just apply the same formula? Or have you lied to me? Is this the wrong formula that you've told me? Technically, it's not the wrong formula, but this is a more complicated case where you're actually expected to get negative integrals or negative definite integrals because you have portions of the graph that are below the x-axis. If you remember with definite integrals, you can actually get negative values, and that's when more of the graph is below the x-axis than it is above. So what you can see in this case is that this part will be a negative integral, this part will be a positive integral, but for areas we always want positive values. So what you actually have to do in this case is split it up into its positive region and negative region, and then kind of add them together. Now, a lot of people, I'm just going to show you like the wrong way of doing it, just to emphasize you're not meant to do this. You're not meant to do this way, but a lot of people would just go straight from 0 to 3 pi on 2 because they say, okay, that's the lower bound, that's the upper bound. My function is sine of x, and this is going to get me my right answer. No, that is going to get you the wrong answer. You don't want to do this way because, again, it doesn't take into account that this portion of the graph from pi to 3 pi on 2 is negative. So you might be asking yourself, how do you actually consider that that portion of the graph is negative? What you have to do is split it up into two areas. So we might call this one A1, we might call this one A2, and we'll just split it into two different expressions for now, just to make it a bit easier to understand. Now, A1 is the easy part, right? Because that's above the x-axis. So what we need to do is just a normal way of integrating from 0 to pi. So you just integrate this from 0 to pi, 0 the lower bound, pi the upper bound, and then we have sine of x dx. And we'll just leave that for now, we'll evaluate it later. Now a2 in this case, a2 is the portion of the graph from pi to 3 pi on 2 that's actually negative. So what we do is we actually make it the negative integral from pi, which is the lower bound, to 3 pi on 2, which is the upper bound. Now you might be thinking, why do we make a negative? It's because we expect this part of the expression, which is the integral from pi to 3 pi on 2, to be negative because it's below the x-axis. So what do we do to make a positive? We chuck a negative out the front, and that double negative is going to make a positive, which is going to find our absolute area, which is actually what we're trying to find. Now, you can see it's a bit messy. You've got the negative out the front, and negatives out the front is never a good thing in algebra because it makes everything a bit more complicated. So what we can actually do is we can keep it as negative and put lower bound to upper bound. That's perfectly fine. But what I like to do is I get rid of this, and I get rid of this as well. Sorry, my finger's smudging it. And I get rid of the negative as well. And what I can actually do is just swap the bounds. So put the upper bound at the bottom and the lower bound at the top. And what that's going to do is by swapping the bounds, it's going to induce a negative factor in our expression, and that kind of negates the need for a negative at the front. So I forgot the terminology, but that negates the need for a negative at the front because I've already swapped the bounds. And that means I just don't have to deal with the negative when I'm calculating my values. Now, what I like about these questions is that it reuses the same integral, so you can actually save a lot of the time that you spend evaluating things because the integral of sine of x is obviously not going to change, and you have some common substitutions, which makes things a bit easier. I'm going to change the pen color just to make it a bit clearer to read. Now, the integral of sine of x, you don't have to memorize this at the moment. Again, it's on the formula sheet, but with practice, you're going to know them all very easily. The integral of sine of x is actually negative cos of x. So I could take this as negative cos of x and then substitute my bounds of 0 to pi. Now again, as I said in the previous part, I don't like dealing with negative values because it does cause a lot of confusion when it comes to calculating things. So what I'm going to do is get rid of the negative and change my bounds here as well. And I can actually do it at this step as well. That's perfectly fine. I just have to make sure that if I do get rid of my negatives, I actually do swap the bounds as well. And I can do the same thing here. Once I evaluate this, I go negative cos of x first, just to illustrate it, and then I'll get rid of the negative once I've done it. So I can see here I've got a negative cos of x from 3 pi and 2 to pi. So I make this positive, get rid of this, 3 pi on 2 to pi. Again, I just got rid of the negative and I'll swap the bounds. It's going to make things a lot easier, trust me, when you're doing the calculation. And when I wasn't doing, year 12 methods, I always told myself, oh, I could just leave the negatives in, it's fine. But you don't understand how many times I got the answer wrong because I didn't deal with the negatives. And you get double negatives, and you see some of these cos substitutions will actually turn into negative values as well. It's going to make it even more confusing. You're going to have negatives upon negatives. It's going to be very messy, and you are going to get something wrong. I assure you of that. So just get rid of them. Don't be stubborn. Humble yourself, and just make sure that you get rid of the negative values and swap your bounds. And it'll just make things a lot easier for you down the track. And you'll see now, when I get these negatives out, it's going to make things a lot easier because, for example, cos of 0 is just 1. Now, I don't have to deal with a negative value at the front. And then cos of pi is actually negative 1. If you imagine a unit circle, pi is there. You can see the x is the cos value, and the x value will be negative 1 at that left extreme of the unit circle. So this will be 1 minus negative 1. You can see, that's beautiful. 1 minus negative 1 is 2. If I left all the negatives from the start, I'm going to have negatives upon even more negatives. I don't want to do that. That's very simple. Now, this substitution here. Cos of 3 pi and 2. Where's 3 pi and 2 in the unit circle? It's there. What's the x value, which is the cos value in the unit circle? That's on the y-axis, so the x value just equals 0 for that substitution. Again, cos of pi is negative 1, so I end up getting that. So now I've got 1 minus negative 1, which is 2, 0 minus negative 1, which is 1. Therefore, I'm left with 2 plus 1, which is 3 units squared. Now, what we can see here is that this portion was 2 units, this portion was 1 unit, and you could kind of see some symmetrical properties here because 3 pi and 2 is halfway between pi and 2 pi, and 3 pi and 2 is just at that peak there. So yes, what I could have done is just calculated this portion here, multiplied it by 3, and I would have got the same answer. Now, with experience, you'll kind of know and see which functions are symmetrical or not. You can see that sine is symmetrical from the top to the bottom, same as coses, and same as you have even function, for example, if you have a parabola or anything like that. So in this case, what I could have done is just calculate that one area, multiplied it by 3. I could have calculated this area and multiplied it by 1.5. You'll notice all these, there's infinitely many ways that you can make this easier for yourself. So Figure out what works for you, make it simple for yourself, and you're going to assure that you're going to get the right answer.